Hi friends, in this video we will see a detail about purlin design. Okay, this purlin, you can see this purlin basically we provide to safely transfer this sheeting load to the rafter. So this is intermediate part of our PEB structure and this GIRT. Okay, these GIRT are provided to hold this sheeting. So these two important parameter purlin or GIRT. So in this video, we will see about purlin, purlin, okay, the purlin material, purlin design, everything we will see in this video. Now let's start with purlin codes, which code we have used. Suppose in this video, I will tell you about with respect to only IS code. Okay. So in this IS 801 1975 cold form purlin design or cold form member we have used with respect to IS 801 cold form purlin design. Second, IS 800 2007. This is for steel design, general construction of steel. Second, IS 875 Part 3. This code we generally use for wind load calculation. So these codes IS 801, IS 800 2007, IS 875 Part 3 basically play important role for our secondary member or primary member also, but in this video we will focus on secondary member. Let's start with some examples. So after the example, you can understand the purlin design. Then I will explain you the detailing of purlin. So here the assumption, our assumption or given data are purlin span between support, purlin span between support. This purlin span or bay length we consider is equal to 4 meter. And second point, the purlin spacing. Purlin spacing. Just we assume 1.2 meter center to center purlin spacing we provided. Now, dead load. In dead load, roof sheet, so roof sheet plus purlin, self weight plus fastener will come, and this dead load 0.35 kilonewton per meter square. Now the third point, imposed or live load is equal to 0.75 kilonewton per meter square. This is according to IS 875 part 2. And wind suction, wind suction or worst case uplift pressure. Uplift pressure we consider is equal to 0.8 kilonewton per meter square. Okay, now we consider the wind suction, dead load, live load, and steel grade. Steel grade of steel we have considered, steel grade we consider Fe 250. It means Fy is equal to 250 Newton per mm square. And for hot roll or equivalent, for cold form use specific material Fy for manufacture IS 801. And limit state design, limit state design, we use partial safety factor gamma m0 is equal to 1.1 for yielding, or gamma m1 is equal to 1.25 for ultimate. This given data we have considered for our PURLIN design. These are a typical example. Okay, uh, for your project and whatever project you design, just consider roof load, dead load, wind pressure coefficient, steel grade according to projects. Different projects have different values. Now, second part, we convert area load to line load on each purlin. Okay, means whatever the area load we consider, that area load we convert into the line load. The line load is line load on purlin is equal to W is equal to area load into purlin spacing. If we multiply area load to the purlin spacing, then we can get the value load on line load on purlin. So first one we convert dead load. Dead load WDL is equal to 0.35 kilonewton per meter square, and our purlin spacing we consider 1.2 meter. So the value will come 0.42 kilonewton per meter. Second, live load W live load is equal to 0.75 into 1.2. Here we get live load 0.9 kilonewton per meter. Kilonewton per meter. Third, wind suction. Uplift line. For that, we calculate W is equal to 0.8. The coefficient we consider for uplift 0.8 into 1.2. 0.8 into 1.2 is equal to 0.96 kilonewton per meter. Now we add all the dead load factor and upward factor. Dead load means this dead load or live load will act downward, but this wind load act upward. है ना? This is uplift force. So just add these two load 0.42 plus 0.9. 0.42 plus 0.9, the value will come 1.32 kilonewton per meter, and 0.96, this act at suction, so 0.96 kilonewton per meter. So this value will greater than 0. Uplift value, so our design is safe. Okay, our consideration is safe. So go into then just take second point. Strength, ultimate design bending, choosing governing load combination. Strength, ultimate design bending. For that, we use as per IS 800 load combination. For strength capacity, according to IS code, we use factor of safety 1.5 dead load plus 1.5 live load. Or for uplift or anchorage check, we use load combination 0.9 dead load plus 1.5 wind load. So these two factors have different. Okay, this is strength capacity and this is uplift capacity if we use with respect to these combinations. Now compute factor line load for bending strength. Compute factor line load for bending strength. WU is equal to 1.5 dead load plus 1.5 live load. 1.5 dead load, the value will come for dead load 0.42 or plus 1.5 into live load. Live load value 0.9. So if we calculate this value, then we can get 1.98 kilonewton per meter. This value we get for bending strength. Now the second point, maximum bending moment for simply supported assumption. We consider this purlin is simply supported, so that's why the maximum bending moment for simply supported assumption. For simple calculation, we generally assume the beam is simply supported. So accordingly, we calculate maximum bending moment. So maximum bending moment here come WU L square divided by 8. WU, the value of WU is equal to this value, okay, 1.98 kilonewton per meter. And the length is 4 square divided by 8. Okay, if you see 1.98 into 4 square, 16 divided by 8, it's 2. and the value will come 3.96 kilonewton meter. So this bending moment value will govern in our simply supported beam. Okay. Now the second point, design strength bending requirement, limit state yielding. For limit state yielding, the design stress value is equal to Fy divided by gamma m0. The Fy we consider 250 or gamma m0 we consider 1.1. So the value will come 227.27 Newton per mm square. Okay. Now the required section modulus Z required. Okay, required section modulus. The formula of these is equal to m divided by Fy divided by gamma m0. So here m 3.96 into 10 to the power 6 divided by 227.27. So if we calculate these, then we can get the value 17,424 mm square, mm cube. This is section modulus. So if we want the section of whatever the section, the Z section or C section, if that section value, the section modulus value of that section is greater than 70,424, then we can use that section for this type of spacing, base spacing. Okay. Then next point, step 2, serviceability. In this we can check this for bending strength. Now we will check with respect to serviceability. Serviceability, it means deflection. Deflection check. Serviceability or deflection check. Now let's start. Let's see the detail. For serviceability, deflection limit for purlin supporting roofing, commonly used, we generally use serviceability deflection for purlin is equal to length divided by 180 or 150. Length divided by 150 for roofing, L by 150. Or this is depending on this will take IS 800 or SP 38, or this depending on cladding brittle. Cladding should be brittle versus flexible. This limit, deflection limit, we have generally considered. Our length should be 4,000 and length divided by 150. Here value we get 26.67 mm. This is limit for our purlin. Okay, this is a maximum limit. If this any deflection value will come below this, then that section is safe. Otherwise, that section will be revised. Suppose the simply supported beam with uniformly distributed load. Okay. Generally, we consider this type of beam, simply supported beam with UDL. Here, the W per meter load will come. This is length. For this simply supported beam, the deflection value is equal to WL raised to 4 divided by 384 EM. So here W will come 1.32. 1.32 uh, pi pi into pi w L here come 4 raised to 4 divided by 384 EI. So E is for steel is 21 2.1 into 10 to the power 5 into I we assume. Okay, I we want to calculate because we have this deflection value, maximum deflection value. Maximum deflection value is here is given 26.67. So accordingly we calculate. So I is equal to pi into 1.32 into 4 raised to 4 divided by 384 into 2.1 into 10 to the power 5 into 26.67. With calculation of all of these, then we can get moment of inertia 7.857 into 10 to the power 5 mm raised to 4. So this is section moment of inertia of section, and section modulus also we calculate, and moment of inertia we calculate. So if the value will if any section have value greater than this 7.85 into 10 to the power 5 mm raised to 4, then we can consider that section can carry uh, bending moment or deflection also. Okay. Now Z is equal to I by Y. Z is equal to I divided by Y. So Y is nothing but distance from neutral axis to extreme fiber. Y is distance from neutral axis to extreme fiber. So the formula is Z is equal to I by Y, or here Z will come 17,424. Okay, or the Z section, suppose we use Z purlin or C purlin with depth of 150 mm. So Y will come here, Y is equal to 75 mm. Okay, so the I is equal to Z into Y will come, or I is equal to Z into Y. So Z value here 7.857 into 75 to the power 5. This value will come 7.85 into 75. I is equal to Z into Y. Z is equal to 17. No, okay, sorry. This I value, or Z value is 17,424. 17,424 into 75. This value come 1.31 into 10 to the power 6 mm raised to 4. Okay. If we consider this section, the value of moment of inertia will come 1.31 into 10 to the power 6. Okay. Or according to deflection limit, the value comes 7.85 into 10 to the power 5. So this I value is greater than I required. We required this 7.85, but we get 1.31 into 10 to the power 6. So this is safe. Okay. But do not exact check with choose section I and Y. Example only, use real section property from manufacturer table. The real value we get from manufacturer table. Now go into the second point. Here we check with respect to strength bendings. Now check with respect to uplift or anchorage check, wind suction. So here the first point for uplift critical case use combination IS 800 IS 875 0.98 load plus 1 plus minus 1.5 wind load. So here the dead load value and wind load value we generally know. So dead load value is equal to 0.9 into 0.9 into 0.42 is equal to 0.378 kilonewton per meter. This act, this dead load will act downward. And second one, wind factor. The value will come 1.5 into wind load. So 1.5 into wind load, the value will come 0.96. So here the value will come 1.44 kilonewton per meter. Okay. This 1.4 kilonewton per meter, this value 1.44 kilonewton per meter is uplift because this is with respect to wind. So now we get the net value. Net value we want, so 0.378 minus 1.44. This value will come minus 1.062 kilonewton per meter. Net uplift, that it means minus it means net uplift will come minus 1.062 kilonewton per meter. The design connection or anchor bolt and rafter attachment to resist this uplift per unit length multiplied by the length of purlin to get total uplift. If you want to get total uplift force, then we multiply this value with total purlin length. Then we can get the total uplift load which act on that purlin. Also check stability of purlin lap, means stability of purlin lap. We use lapping in purlin also. Okay. This purlin, this lap. So we check also this purlin lap stability, clip, purlin end fixing. Use I-75 wind pressure calculated. Okay. Now after that, this is uplift, very important for purlin design. Now fourth point, shear check. Shear check is very important. This parameter is also very important. Shear check is nothing but shear at mid-span for simply supported, uniformly distributed load is small for purlin span, maximum shear at support. Okay. Actually, we consider the simply supported beam, so that's why the maximum bending moment will occur at center and maximum shear force act at the support. Here maximum shear force act, or here maximum bending moment. at center or at support. This is bending moment diagram, or this is shear. For shear check, the maximum shear at support, because we consider our simply for purlin the beam is simply supported. That's why we consider the shear force at maximum at support. So that's why the maximum shear at support Vmax is equal to WU L divided by 2. Now the WU value have 1.98. Okay, we calculate 1.98 into length 4 divided by 2. This value will come 3.96 kilonewton per meter, kilonewton maximum shear force. The shear capacity of typical purlin cross section is usually adequate, but check web shear capacity with design shear formula. Okay, for this is for section. Okay, but check for uh, check for web shear capacity according to IS 801 or IS 800. Consider web thickness and shear buckling for thin web. So accordingly, we get the shear capacity of web section also. So this is important checks if we design any type of purlin. I hope you understand this comes steps procedure. Okay. Now I will tell you some important points. Check if you want to real section property, then first point, always check manufacturer table. Manufacturer table. In that cold form Z or C Purlin catalog, which lists depth, thickness, area, IXX, ZXX, and weight. These values are mentioned in manufacturer table. Accordingly, we can select the section properties. Many suppliers publish this example catalog or technical table exist online. Use those to pick up section. Okay. In this example, we see the Z value will come 17,424 or moment of inertia 7.86 into 10 to the power 5 mm raised to 4. So use that these sections. Or if we prefer hot roll channel section. In IS code, we have two sections. Hot roll channel section. Hot roll channel, that means ISMC, Indian Standard Medium Channel section. IS section table IS 808 we use. IS 808. IS 801, that is for cold form section, and IS 808 for hot roll Purlin sections. Typical ISMC channel often much larger Z than required for small span. They may be heavier than necessary. Okay. This section property and section modulus have higher. That's why we don't use this hot roll channel section for smaller smaller base span of PEB structures because it's uneconomical for small span. And third point, the check combine bending plus compression if purlin is laterally unsupported. Okay. If purlin is laterally unsupported, then we check that for combined bending plus compression. Check buckling local and oral using IS 801 for cold form or IS 800 for hot roll. Or fourth point, provide sag rod. Sag rod or intermediate ties. Sag rod or intermediate ties. If a span is greater than or equal to 4 to 4.5 meter. For limit lateral stability, many manufacturers advise anti-sag rod for longer span. So this 4 point always remember for our calculation. Now I will explain you how we get this cold form and hot form members and what is this cold form and hot form members. That is very important. Huh? Hot form steel and cold form steel. Okay, this hot form steel, if you see the hot form steel roll at high temperature, the hot form steel is roll at high temperature. And here the above, that is above recrystallization. That means that doesn't regain its shape. This hot roll section are ISMC, ISMB, or ISA Indian Standard Angle section or rectangular hollow section. This section are hot roll section. And cold form members are roll or press. In this we use technique roll or press at room temperature. In hot roll we roll at high temperature, but in cold form we roll or press at room temperature. It's below recrystallization. Like Z or C purlin, Z or C purlin we use. This is light gauge channel. Second point, the thickness of hot roll steel are vary from 5 to 25 mm, or cold form member have thickness 1.2 to 3.15 mm. The third point, these are open or closed section, and channel section have Z or C. Or for this we use IS 800 2007, or for this IS 801. And fabrication, this usually welded or bolted. Both we use welded or bolted. But if we use cold form member, then it should be bolted self-drilling, screws, self-drilling screws, or it should be not be welded. Okay, secondary member we cannot weld. Or the surface finish of hot roll section, it's uncoated, or generally we paint or galvanize upper layer, paint or galvanize. Okay, or this cold form member we usually pre-galvanize. Or corrosion resistance. The yield strength of this hot roll section are vary from 250 to 350 megapascal, but cold form member have higher yield strength. That yield strength 350 to 550 megapascal. Okay, the yield strength vary. Now there are very uh, different points. This hot roll PURLIN we generally use economical economical less than or equal to 4 meter base spacing, or these are economical up to 7 to 8 meter. Okay, if our base spacing 7 to 8 meter, then we can use this cold form member lapping, uh, purlin, or this with lapping, with lapping or continuous, both is available. Or this hot roll member have higher weight, heavy section, or this cold form member have light section available because of the thickness is very low. Okay, in this we provide lateral support with single span, and in cold form member we use lateral support with sag rods or ties, or if you see this hot rod section have less sensitive in stiff because they have stiffer or thicker. But if you see in deflection, a deflection criteria we see, if you see cold form member, these have must check carefully because these have thin webs, can deflect or buckle. That's why we use this section property according to economical or spacing. Cold form Z or C GIRT prefer for regular PEB walls. Hot form channel only when heavier loading. Example, crane bay walls, blast walls, or tall industrial facades, we use hot form channel. Otherwise, we generally prefer PEB, cold form PEB structure for walls. For packet, we use hot form channel section. And second important point for main structural bracing. For with respect to bracing, I will tell you the for main structural bracing, stability of frame, use hot form angle bracing. For roof, wall, diagonal bracing of sheeting, cold form strap or rod is sufficient. For purlin, we use cold form member. For GIRT, we use cold form member. For bracing, we use hot form members. Okay. And for primary beam or column, we always prefer hot form member. So this is very general guideline our PB structure. Now I hope you understand all the point, and if you have come any doubt and difficulty, please let me know in let me uh, send detail what type of difficulty you arise if you design PV structures. Then we will solve that problem. Okay. Now we will meet in next lecture.